All right, so we want to thank everyone for showing up for our CHEMSEM this afternoon. Our speaker is Dr. Jennifer Bergner, and she's an assistant professor and Chevron chair at UC Berkeley Chemistry Department. She completed a PhD at Harvard. This was recent, right? You've been at Berkeley for at least a year, 2 years?
Yeah, I've been at Berkeley for 1 year now.
1 year, 1 year. So getting started. And then she did a NASA Sagan postdoctoral fellowship at University of Chicago. You could have driven up to see us.
Yeah, should have invited me sooner.
I know. And she's an expert in astrochemistry and planet formation. Today, in addition to our usual chemistry crew, we welcome our physics guys. Thank you guys for joining us. It's exciting. So, Professor Bergner, the time is yours.
Great. Well, yeah, thanks again for having me. I should say first, my background is in chemistry. All of my degrees are in chemistry, but I've spent a lot of time in astronomy departments, and I think there's a lot of really exciting work happening in these kind of interdisciplinary fields right now. So never feel limited by the degree you happen to have. Okay, so I'm going to talk about chemistry that is ongoing during planet formation. And I want to start this story actually maybe 50 or 60 years ago, when astronomers started building these huge radio telescope dishes and then pointing them to regions in space where stars are forming. And it was a big surprise at the time because everyone thought that space was too hostile for molecules to form, but they started detecting these small molecules like ammonia, formaldehyde, hydrogen cyanide, and then within a couple of years, they were detecting things like methanol, cyanoacetylene, acetaldehyde, so bigger molecules. So in the early 70s, there was this sort of flurry of review articles describing this newly discovered interstellar organic chemistry. And within these review articles, people started to take notes that these small to mid-sized organics that they were finding in interstellar space are at times the same ingredients that are needed for prebiotic chemistry schemes in early Earth scenarios. So this was sort of the beginning of some speculation that interstellar chemistry could have some connection to origins of life chemistry. Now, if you fast forward to where we are today, we understand now a lot more about how this interstellar chemistry works and how planets form. But this basic idea remains a big motivation of what astrochemistry is interested in doing. And the idea is that if we can study the chemical environment that stars and planets are forming in, we can learn about how prebiotic building blocks are delivered to new planets. So what do I mean when I say a prebiotic building block? There's a couple of ways that we can think about this. On one end of the spectrum, we could think about just the simplest sort of elemental ingredients that are needed for organic chemistry. So here on Earth, most biology makes use of this small basis set of elements: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. So we might just be interested in understanding what the inventory of these biogenic elements is that's incorporated into a planet as it's forming. And to answer this question, we just need to measure essentially the bulk composition of the solids and gases that are forming the planet. At the other end of the spectrum, though, we know that there's this wealth of chemical complexity present in interstellar regions. So we might wonder whether any of these prebiotically useful molecules can actually be delivered intact to planetary surfaces. Now, planet formation is a really violent energetic process. And so molecules that are incorporated into the planet while it's forming aren't likely to survive, but you could deliver interstellar molecules to planets through impacts of icy planetesimals that form far out in the protoplanetary disk. And they're stored at such low temperatures that they can preserve their chemical composition. And then later these planetesimals impact terrestrial bodies and can bring along their volatile reservoirs. So this is how you would have to have a scenario of actually delivering these organic molecules intact. Okay, so here on Earth, we don't know whether life started sort of fully from the ground up, or perhaps with this jump starting of delivery of interstellar organic molecules. So it's useful for us to try to consider both of these perspectives when we're thinking about the chemistry of planet formation. Now, it's an especially exciting time to be thinking about planet formation chemistry because right now astronomers are discovering dozens and dozens of new exoplanets, some of them which they think are potentially habitable. So this is an artist's impression of a little gallery of nearby exoplanets that seem to be rocky in composition and have sort of lukewarm temperatures to maintain liquid water. So this is an exciting prospect, but we're still really in the very early stages of characterizing exoplanets. And so our understanding of what makes an exoplanet habitable right now is quite limited. Ultimately, in addition to being a rocky planet with the right temperature, we would like these potential Earth analogs to also inherit the chemical ingredients needed for habitability. And so we can study the chemistry of planet formation to try to understand how planets are seeded with these elements. Okay, so I'm going to spend a few minutes now talking about how we actually go about studying planet formation chemistry. There are a lot of different considerations to keep in mind here, so I'm going to use this schematic to walk through some of the different pieces of information that we can bring to study this very interdisciplinary question. Okay, so the first consideration is the fact that at the very low, or the extreme conditions of interstellar space, the volatile molecules that we're interested in can either exist in the gas phase or as ices. And it turns out that in the gas phase, the very low temperatures and densities put some really stringent constraints on the types of reactions that are actually possible. So because of these low temperatures and densities, we must have exothermic, barrierless, and two-body processes. This leads to the production of these really kind of odd-looking but interesting molecules, like these very unsaturated carbon chain molecules that form would never be stable on Earth, but we see them present in the interstellar medium in the gas phase. So this is chemically quite interesting, but from an origins of life standpoint, maybe less relevant. Instead, we think a lot of the organic molecules that we're seeing are forming in the ice phase. And what I mean by this is in interstellar space, we have these refractory dust grains made of things like silicates and carbonaceous material. And when it becomes cold and dense enough, volatiles will freeze out of the gas phase onto the surfaces of these dust grains and build up what we call ice mantles. So these include not just water ice, but things like carbon monoxide ice and nitrogen ice and carbon dioxide ice. And within the ice phase, you can actually get around some of the constraints on the chemistry that are operating in the gas phase. And so it's really ice phase chemistry that we think is leading to the production of organic molecules in interstellar settings. A note of terminology within the astrochemistry community, we call something a complex organic molecule, or a COM, if it's about 6 atoms or bigger. So the terrestrial chemists will always laugh at us, but this is really kind of the higher end of complexity that we're able to access through purely remote methods. Okay, so the next important thing is that we can study the chemistry of these ices and gases along the entire sequence of evolution that leads to the formation of a solar system. So this process kicks off in a molecular cloud, just an overdensity of gas and dust within the interstellar medium. You have a perturbation that leads to gravitational collapse and causes the formation of a protostar that's still embedded in its parent envelope. As the protostar evolves, it will form a rotating disk around the central protostar. And eventually the disk will sort of, or the system will clear away any material that isn't left in the protostar or the disk itself. And it's within these protoplanetary disks where we actually finally have high enough densities for solids to start sticking together and for the actual physical process of planet formation to take place. And then eventually things that aren't put into planets or the star are blown out, and we're left with a planetary system like our own solar system. So if we're interested in understanding chemical processes during planet formation, we're kind of primarily interested in the protoplanetary disk because this is where planet formation is happening. But it also turns out that the disk is inheriting a lot of its chemistry from earlier stages of star formation. So we would like to sort of think about the whole sequence of chemical and physical evolution leading up to protostar and protoplanetary disk formation. And we can also look within our own solar system. So there are primitive relics like comets and primitive asteroids that are minimally processed materials left over from the beginning of our solar system. So the time when planets were forming within our solar system. And so we can study the composition of these materials to try to understand what the solar system looked like when it was in its protoplanetary disk stage. And I won't go into too much details, but basically when we look at the chemistry of these bodies, we see evidence that there's a very complex chemistry at play in our solar system that we can try to understand better by looking at these analogs around other stars. Okay, so we have a couple of tools that we can use to try to study planet formation chemistry. This is sort of the trifecta of astrochemistry is lab experiments, observations, and modeling. So observations, this is when we use telescopes to get direct constraints on both the abundances and distributions of molecules that we can observe through remote methods. And this also tells us, in addition to something about the chemistry, we can learn about the physical conditions present in these star and planet forming regions. We can use lab experiments to make measurements of the microphysics and chemistry that would take place in these extreme environments using very controlled Earth-based settings. And then we can use models to make predictions for how chemistry should play out on sort of astrophysical timescales with a lot of sort of complex physical processes happening. So these different approaches all sort of work in tandem to give us the best picture possible of planet formation chemistry. All right, so I'm going to spend just a couple minutes talking in more detail about the observational side of astrochemistry, because most chemists are familiar with spectroscopy, but might not have thought about how it could be applied to study compositions of objects that are very far away from us. So when we're thinking about the chemistry of a protoplanetary disk, for example, there are molecules present in a range of different environments, and we can use different kinds of observations to give us access to these different physical regimes. So you can imagine next to the star, the gas is very hot. As you move away from the star, things cool down. And if you move far enough away and into sort of the densest region of the protoplanetary disk, the volatiles are present not as gases, but as ices. So we'd like to access all of these different reservoirs. We can look at the hot gas using infrared telescopes. So this is basically doing vibrational spectroscopy. And you can see here an example from the recently launched James Webb Space Telescope, where you can see sort of this broadband silicate emission feature, and then superimposed on that, you see the row vibrational features from molecules like CO, water, and CO2. So this tells us something about the hot gas. We can access cool gas with millimeter astronomy or millimeter telescopes. So in this case, we're looking at rotational spectra of cold gas phase molecules. And this is an example of the kinds of spectra that we would get in the millimeter, telling us about the inventory of molecules present in the cool gas. And then lastly, we can access the ice using infrared telescopes again. So we have to look for the ice, not in emission, but in absorption. But you can think of the star as providing sort of a backlight of infrared emission, and then superimposed upon the stellar infrared flux, we have these absorption features corresponding to the vibrational modes of condensed species like water, CO2, and CO. Okay, so with these different observational methods, we can access different components of the volatile reservoir in these planet-forming environments. So in addition to this like multi-wavelength coverage, what's also been really exciting recently is that we have better and better spatial resolution. So we can now really zoom into imaging the composition of gas and ice on spatial scales that are really relevant to solar systems. So this is a comparison showing the capabilities of a millimeter telescope called ALMA. That's really the state of the art. It's down in Chile on top of a very high plateau. And on the right, you're looking at three images of molecular line emission. So it's the same molecule imaged towards the same disk. But over time, our spatial resolution is getting better and better, and we can start to really distinguish this weak kind of emission and see actually really interesting substructure in the distribution of molecules in the gas. So we're getting an incredible amount of detail about how molecules are sort of distributed across these forming solar systems. Similarly, at infrared wavelengths, we now have James Webb, and so this again is showing you an image of a protoplanetary disk. You're looking at it edge on, so you can see sort of a top surface and a bottom surface from a flared disk structure. But again, actually being able to spatially resolve the emission is a really exciting and new thing for us. Okay, so now hopefully you have an understanding of a lot of the different pieces of information that we can bring to study this question. And I'm going to walk through a couple of examples of kind of exciting applications of astrochemistry and planet formation in recent years. Okay, so we'll start by thinking about what's happening in the ice phase. Again, James Webb has been really powerful for giving us a new view of the ice compositions in star and planet forming regions. So this is showing a really beautiful image from James Webb of a young star, and you can see at the center this sort of dark lane. So that's the protoplanetary disk actually that we're seeing sort of its shadow. And then there's these very dramatic kind of bright outflows that are being launched away from the young star. So we're getting these beautiful images, but as chemists, we care not just about images, but about spectra. And so this is really where James Webb is giving us a lot of new information. So this is the spectrum in the mid-infrared taken towards one of these young protostars with James Webb, okay? And you can see, again, like I said before, we have some sort of continuum of infrared emission, and then absorbing away from the continuum, we see these features corresponding to molecules in the ice phase. So things like water, ammonia, methanol, and so forth. And so if we think about what's present in these ices, we see a lot of quite simple molecules, things like water and CO2. But if we zoom in and look at the detail, we see actually all of these little bumps and wiggles that tell us that there's not just simple molecules that are present in these ices, there's actually pretty complex things. So there are ammonium salts, formic acid, ethanol, acetaldehyde. And so a big kind of challenge for our field is explaining how you form these larger organic molecules within the ice phase. So to understand ice phase organic chemistry, we have to think about the processes that can go on within the ice. So we can populate and depopulate our ice using or by accreting new molecules or desorbing molecules from the ice surface. Within the ice, you can have diffusion or reaction of molecules to form new species. And then photo processes are also very important for us. So if you send in the right energy radiation, you can break apart molecules or even kick them back into the gas phase. So ultimately, we need to understand how these different microphysical processes are working to explain how organic molecules are forming. Fortunately, we can reproduce these physical conditions in the lab to try to understand this chemistry. So this is a photo showing the instrumentation I worked on actually during my PhD. So it's an ultra high vacuum system. We're reaching very low pressures, around 13 orders of magnitude below atmospheric pressure. And we can achieve temperatures down around 10 Kelvin. And so within this setup, we have different instruments that we can use to form analogs to interstellar icy material and then study the way that chemistry proceeds. So on the right, you're looking at a schematic. There's a vacuum chamber, it's this sort of big circle. We have a helium cryostat that is cooling down a sample window to very low temperatures. We allow gases into the chamber, which condense onto this very cold window. And then we can study the composition of the ice sample in situ using infrared spectroscopy. We can also keep track of what's going on in the gas phase in the chamber using quadrupole mass spectrometer, and then we can use light sources to stimulate chemical processes if we need to. So the question that we're going to think about for a few minutes now is what ice phase pathways are leading to the production of complex molecules, even in very cold interstellar conditions like these protostellar envelopes that we're seeing with James Webb. Okay, so one pathway that I think is showing some particular promise in recent years has to do with excited state oxygen atom chemistry. So what I mean by this is when you energetically process oxygen-bearing ice molecules, things like carbon monoxide, carbon dioxide, or water, and you break them apart, you will tend to produce an oxygen atom that's in an electronically excited state, or an O singlet D atom. So in the case of irradiating CO2 with Lyman alpha photons, you would break the molecule apart, forming carbon monoxide and one of these excited oxygen atoms. So this process has been really well studied in the gas phase, and we know that in gas systems, these excited oxygen atoms can actually insert directly into the CH bond of hydrocarbons, allowing you to form an organic molecule directly from a hydrocarbon. In the gas phase, we know that this process has basically no energy barrier, and we have a very favorable kind of exothermic formation of the methanol product. But in the gas phase, because there's not a third body around to sort of dissipate this energy, you typically fragment the methanol product back into radicals. So you can't stabilize this product, and you don't end up increasing chemical complexity as a result of this reaction. So we wanted to look at how this oxygen atom chemistry proceeds when you're in the solid state. To do this, we sort of selectively dissociated oxygen molecules within an oxygen-methane mixture. And then here I'm going to show you sort of the time series of the infrared spectrum over the course of the experiment. So on the top, you can see in the infrared, the peak corresponding to methanol is growing over time. And we've just quantified that on the bottom with this growth curve showing the yield of methanol over time in the experiment. So what we can do with this is we can develop some simple kinetic models that describe the reaction rates of methanol formation. We fit this model to our experimental growth curve, and we pull out these reaction rate constants. Now we can plot these reaction rate constants as a function of temperature. And if you're familiar with Arrhenius relations, then we know that essentially the rate constant should have an exponential dependence on the activation barrier divided by the temperature. So if we were to see a slope in this plot, that would tell us what the activation barrier to this process is. Ultimately, when we run this chemistry at many temperatures, we see no temperature dependence, telling us that, like in the gas phase, this reaction is proceeding without an energy barrier. Okay, so this is really good news if you want to form methanol in very cold interstellar regions. You can have this photochemically active process that has no temperature dependence and is just as efficient at 10 Kelvin as it would be at higher temperatures. So with these kinds of experiments, we can also look at other processes that are happening in the ice. We're not just forming methanol, but other carbon-bearing molecules like formaldehyde, CO, CO2. And we can try to develop reaction networks that describe how all of these different species are related to one another within our ice experiment. We can derive branching ratios, which is useful for astrochemistry models. And ultimately, we'd like to explain the formation of things bigger and even more complex than methanol. So we set out to look at how these excited oxygen atoms react with the C2 hydrocarbons. So you have ethane, ethylene, and acetylene. And we see that in all cases, we have this sort of barrierless insertion process leading to the formation of a whole suite of different oxygen-bearing organic molecules. So if we go back to this James Webb spectrum, we can see that a lot of the molecules that we're forming through this oxygen atom chemistry, things like ethanol, and acetaldehyde, and formaldehyde, are things that are showing up in these interstellar ices. So it's exciting that this kind of process could be contributing to the formation of organic molecules in very cold early interstellar contexts. Okay, so we've talked a little bit about how to form organic molecules in the early cold stages of star formation. And it turns out that we really care about this because, like I said before, we think that there's actually some inheritance, chemical inheritance of material from the early stages of star formation all the way through to the planet formation stage. So we see some evidence for this when we look at the composition of comets in the solar system and compare them to the organic compositions of these young protostars. And this is just showing sort of a very nice correlation between the organic reservoirs in a solar system comet and a protostar. So this is just one line of evidence that suggests to us that the material that is making its way into planetesimals in the solar system actually may have been formed well before the sun was even born. So that sort of raises the question, if a lot of interesting chemistry is happening very early on, what is actually the role of the protoplanetary disk stage in influencing the composition of forming planets? Okay, so this is now looking at sort of gas phase emission of complex molecules towards protoplanetary disks. We're looking at methyl cyanide, which has now been detected actually since ALMA came online in 2015. We've detected it towards a small handful of protoplanetary disks, essentially everywhere that we have observed with enough sensitivity, it's been detected. You can compare this to methanol, which is our kind of usual organic molecule that we tend to detect at earlier star-forming stages. And what's really peculiar is that methanol has only been detected towards one protoplanetary disk. So there seems to be something kind of interesting going on in the protoplanetary disk stage, where this sort of usual suspect of the organic molecule that we see everywhere else is suddenly missing. So to show this a little more graphically, this is showing the methyl cyanide to methanol ratio, where it's been measured in the one protoplanetary disk. We have two useful limits. And if you compare this ratio to earlier star-forming stages, you see we have about a 2 order of magnitude enhancement in the methyl cyanide to methanol ratio in what's actually a very short period of time. So we can say that protoplanetary disks seem to be quite enhanced in nitrogen organic molecules compared to oxygen-bearing organics relative to earlier stages of star formation. And there's a pretty nice explanation for why we would expect this. And it has to do with basically how the physical and chemical evolution of a protoplanetary disk is coupled. So the idea is you start with a young protoplanetary disk, you have small dust that's sort of dispersed throughout the entire vertical extent of the disk. And as the grains grow, they begin to settle towards the midplane, and the grains are coated in ices. So they're bringing their ices with them to the midplane of the disk. And this leads you to have a midplane that's very rich in things like water ice. And the atmosphere of the disk is very depleted in gas phase oxygen. So the net effect is that we're basically taking oxygen out of the surface of the disk and sequestering it in the midplane due to grain evolution. The other effect that happens as grains grow is UV radiation can penetrate deeper into the disk. So small dust grains absorb most of the UV radiation, but as your small dust grains grow to larger dust grains, the UV can penetrate further in and drive chemistry throughout a further extent of the disk. Okay, so models tell us that when you pull oxygen out of the gas and you throw in a lot of UV photons, you should promote a very reducing chemistry, and that should lead to the formation of molecules like nitriles and hydrocarbons. So qualitatively, we can understand then how you would end up with this sort of exceptionally bright emission of molecules like methyl cyanide in protoplanetary disks as a result of this sort of distinctive oxygen-poor, UV-rich environment. Ultimately, though, we would like to systematically understand whether this kind of chemistry can explain the emission patterns that we're seeing in protoplanetary disks. So we set out to survey the chemistry in a relatively large sample of protoplanetary disks. These observations are difficult to make, so 14 disks is actually a pretty big sample for us. And here I'm just showing a gallery of the emission of our hydrocarbon tracer, C2H, our nitrile tracer, HCN, and our oxygen tracer, CO, towards a subset of the disks in our sample. And we can see, again, it's really staggering that you can sort of image the distribution of molecules on these forming solar systems, and we see quite a lot of diversity in the morphologies of the emission. So some molecules look very different between different protoplanetary disks. And sometimes, even in the same disk, different molecules have a really different emission pattern. So this is telling us that there is a really complex chemistry going on within these protoplanetary disks. Okay, so we wanted to take this beautiful emission and turn it into something a little more quantitative. So we can actually model the spectra that we get for the molecular line emission and use that to extract molecular abundances of the molecules that we're interested in. So here I'm showing the abundance of C2H relative to HCN within our sample of protoplanetary disks. And you can see actually that there's a really nice positive correlation in their abundances. So this tells us that disks that are making a lot of C2H are also making a lot of HCN, and they seem to have quite a connected formation chemistry. This then fits actually exactly with what we were expecting from this framework I mentioned a minute ago, which is that when you pull oxygen out of the gas and you have a lot of UV photons around, you should simultaneously promote the formation of molecules like nitriles and hydrocarbons. So it's very exciting then that with these larger samples that we've been able to get in the past couple of years, we can actually start to test the underlying chemical mechanisms that are driving the formation of new molecules in protoplanetary disks. Okay, so in addition to statistical samples, what we're also able to do now is to zoom in with higher spatial resolution than ever before to really map out the distribution of different molecules across a protoplanetary disk. So this is just an example for the CN and HCN molecule, two of these small nitriles. And I won't go into much detail here, but once we have this kind of spatial resolution and can really see in great detail how the emission is varying across a disk, we can start to understand again, sort of mechanistically, what physical processes are driving the production of these nitrile carriers. So just a kind of fun sort of side note about nitrile chemistry, it turns out that in a lot of prebiotic chemical schemes, small nitriles really are a critical ingredient in prebiotic synthesis, leading to molecules, precursors of things like RNA, protein, and lipids. So this is a prebiotic chemical scheme from the Sutherland group, and you can see sitting at the center of this is hydrogen cyanide. It reacts really efficiently to build up carbon backbones, and so it's a really useful kind of feedstock for prebiotic chemistry. So the fact that we're seeing that basically the environments within protoplanetary disks seems to be uniquely efficient at producing nitriles relative to earlier stages of star formation. It's only once we get to the disk stage that we have the oxygen poor and UV-rich gas that leads to this very robust nitrile chemistry. So it's sort of interesting to think that maybe we have sort of during the assembly of planets, the right conditions around to be forming this prebiotically useful precursor molecule quite efficiently. One question we have, though, is the emission that I was just showing you is in the gas phase, right? So we see this bright gas phase emission of nitriles. How does that correspond to the icy material that we know we need in order to deliver to planetary surfaces? So this question is ultimately a question of how efficiently does hydrogen cyanide or small nitriles accrete and desorb onto ices. The incorporation of gas phase molecules into icy planetesimals will essentially be controlled by this microphysical process. So it turns out until recently, we knew very little about the desorption behavior of HCN ice. Hydrogen cyanide is very good for prebiotic chemistry, but very nasty for existing life. So a lot of people don't like to work with it. But we set out to measure its sublimation behavior to be able to answer this question. There are a couple of different ways that you can imagine sort of binding within an ice. You could have hydrogen cyanide binding to itself. You could have it binding to the dominant component of these ices, which is water, or you could even have it actually sort of mechanically trapped within water. And the reason that this works is that we're not talking about crystalline, well-ordered ices here. The structures of these ices are what we call amorphous, so they're very fluffy and porous. And within a water-dominated ice, you can actually trap small volatiles even past their sublimation temperature. So what we can do is experimentally, we can measure the desorption rate of molecules as we increase the temperature of our sample and use this to extract the binding energy of the molecules. And then this will tell us sort of where in a protoplanetary disk should hydrogen cyanide adsorb or desorb. So what we find is here I'm going to show you the results sort of in the context of a solar system like analog. So you're looking on the x-axis at distance from the star, and we have these two regimes that would correspond to sort of where in the solar system you would form icy asteroids or icy comets. The binding of hydrogen cyanide to itself will, or the sublimation of hydrogen cyanide to itself will happen here sort of around 4 astronomical units. Binding to water, that's a little bit stickier, and so it will kind of push the sublimation front in a little bit closer. And the sort of interesting thing here is that these binding energies turn out to be really high. So if this is the sublimation front of water, then basically almost everywhere in the disk where water is an ice, hydrogen cyanide will also be an ice. And we can also measure sort of how efficiently HCN will be entrapped in water. It turns out to be quite efficient. And so moving through this quickly because I want to finish on time, but essentially the punchline here is that we can retain hydrogen cyanide within disk ices almost anywhere where water-rich planetesimals are formed. So we think this is good news if you're trying to essentially incorporate this molecule into icy planetesimals and ultimately deliver it to planetary surfaces. Okay, so I have talked a lot about carbon, hydrogen, nitrogen, and oxygen. But I also want to briefly note that there's some really interesting work being done on trying to understand the phosphorus and sulfur chemistry in interstellar space better. Until recently, we've had a really hard time characterizing phosphorus and sulfur chemistry because these elements tend to be locked up in refractory material. So we've had a couple of successes detecting phosphorus carriers in recent years. This is what we call single dish data. So we have no spatial information, but we detected these carriers PN and PO towards a sun-like star forming region. Based on what we learned from that, we've made 5 new detections of phosphorus-bearing molecules, and we've actually started to map out the emission of these phosphorus molecules. So ultimately, we would like to kind of continue to understand better how actually phosphorus is stored in the interstellar medium and in what form it's present in the sort of building blocks of planets. Okay, I'm going to skip this part in the interest of time, but we're also able to use James Webb to basically get constraints on the ice composition in protoplanetary disks, and that's telling us some really interesting things as well. So to wrap up, I showed you that we can use both statistical surveys and high-resolution observations to try to understand the gas phase chemistry in disks. We see that these prebiotically interesting nitriles seem to be made in abundance. I skipped through this, but James Webb is giving us really the first view of icy material in protoplanetary disks, and we're able to actually get a lot of information out about the volatile reservoir of disks through these observations. And then experiments are also playing a really critical role in helping us to interpret the observations of both gases and ices that we observe in sort of star-forming environments as well as our own solar system. So with that, I'm happy to have a little discussion and take any questions.
Okay, thank you. questions, you could either put it in the chat, Ian is right on it. Why is the window made from cesium iodide? And how did you make a solar system analog?
Um, so the window is made from cesium iodide because cesium iodide is infrared transparent. And so if we want to take measurements of the ice composition using transmission spectroscopy, we need to form the ice on a material that doesn't absorb all the infrared radiation. Making a solar system analog, I'm not entirely sure sort of what that question is referring to, but if you can clarify, I'm happy to have a stab at it.
Okay. Ian, you could clarify. In the meantime, I was kind of interested. I think a lot of us have seen Carl Sagan on video,
Mhm.
but it was interesting to me to see a paper written by him. It was 1972 on interstellar organic chemistry. So that was just interesting to me. One of my questions though is Pluto a planetismal? What
Yeah,
is Pluto? Because I'm learning this word for the first time, planetismals.
yeah. So Pluto, I think you would call like a minor planet or a dwarf planet. It's sort of a little, so when I say planetesimal,
Yes.
I am referring to things like comets and asteroids, which are maybe kilometer scale. So Pluto is bigger than your
Right.
average comet, but
Okay.
smaller than your average planet.
Okay. Okay. All right. Other questions? I have another one. So you use IR in spectroscopy quite a lot, but is there any use for Raman spectroscopy? Because that could pick up some symmetrical molecules.
Mhm.
Do you guys in astrochemistry use Raman?
It hasn't been as common. There are some groups that are, I think, starting to, in a laboratory setting, starting to use Raman for characterization. We obviously can't really use it from a remote sensing standpoint. But I think, yeah, from the lab perspective, it could certainly help you to characterize infrared inactive species in the ice.
Mhm. Okay. Do you see O2 and N2 molecules?
Well, we can't detect them spectroscopically. So we expect that they're present, especially based on people build models where they try to simulate all the processes that should be happening. And they expect O2 and N2 especially should really be a major carrier of nitrogen. But it's impossible for us to detect, unfortunately.
Why?
So as homonuclear diatomics, they have no spectroscopically active modes
Right.
that we can access.
Right. So that kind of is related to another question in a way. Where does the HCN come from? Is there a mechanism, because you talked about it a lot,
Mhm.
but is there a mechanism for the formation of hydrogen cyanide?
Yeah, so there are probably a couple of competing pathways for making HCN. You have to start by breaking apart molecular nitrogen. And so that's one of the reasons where we tend to see HCN in these really photochemically active regions is it's not going to be sort of a product of a very cold quiescent chemistry. You need to have enough like energetic sources present that you can break apart N2 and then have the reactive nitrogen atom go on to probably react with some sort of hydrocarbon fragment to form HCN.
Okay. Okay. Go ahead.
Or any other source for oxygen.
Is there any other source for oxygen other than O2?
Well, water is probably one of the most important oxygen carriers. It's the most abundant molecule that we see on ice grains. And it's actually, if you think about sort of the initial formation of molecules, everything starts as atoms. And there's a lot of hydrogen is way more abundant than any other atom. And so if you have atomic oxygen around in sort of a bath of hydrogen, you're bound to make a lot of water. So that's why we actually have a lot more water than O2.
So I don't, pay attention to HCN a lot, but since you were talking about it, it seems like hydrogen bonding actually between HCN molecules is one of the ways that they could absorb, aggregate, as well as hydrogen bonding between water and hydrogen cyanide. And that could also be the beginning of some reactivity because the hydrogen bonding could actually activate, for example, the cyanide to react with other things.
Yeah, pure HCN is known to polymerize really
Okay.
efficiently. So when people irradiate HCN ices, they often find that, yeah, kind of that process will kick off.
Okay. Ian is at it again. Did you see? Did you? No, your mind is working. Did you see any other isotopes from phosphorus?
We have only detected the most abundant isotope of phosphorus so far. It's already really challenging to detect phosphorus, so at least for the near term, we don't have great hopes of doing any sort of isotope specific measurements, but maybe as our telescopes keep getting more sensitive, that will be something to look at.
So the phosphorus isotopic distribution in the interstellar medium is the same as on Earth?
Is the phosphorus isotopic distribution in outer space as the same, is it as the same on Earth?
I don't know the answer to that off the top of my head. It should be similar to the isotope composition in the sun, at least, but there was a lot of fractionation that happened during the formation of the planets. And so isotope ratios that actually made their way into the planets are often different from what the solar isotope ratios are. So I don't know, I don't remember the phosphorus ratios off the top of my head, but for a lot of other elements, the more important distinction is between the sun and the planets.
Okay.
I have a question she may not be able to answer, but is our sun currently, and it may be a stupid question, but is our sun making some heavier elements like carbon and oxygen currently? Is our sun in the proper position to make these elements? And just curious.
I didn't quite hear that.
Yes, so is our sun currently making some of the heavier elements
Just, the carbon.
like carbons and oxygen, nitrogen?
I know you may not be able to answer.
Yeah, that's a little bit out of my normal wheelhouse. I mean, all of the elements heavier than hydrogen and helium were formed in stars, but I think it might be later on in their lifetime that kind of nucleosynthesis happens. But yeah, I don't want to misspeak, so don't take that as hard truth.
So we know that planets have different sizes, but what is sort of like the minimum size for a planet, and how long does it take for planet formation?
So I don't think I don't have a good answer for the first one. Part of what also distinguishes planets is like something about their orbits.
Okay.
So there are dynamical considerations in addition to size considerations, but we know so we can look at the lifetime of protoplanetary disks around other stars, and we know that they stick around for something between maybe 3 and 10 million years. And that sets the time limit for planets to assemble. So some planets may form faster than that. But anything that isn't done by a few million years is sort of out of time.
Oh, okay.
Ask you what the I'm just curious, she may have said this, but I think, like, what's the concentration of these organic materials around the total planetary disk? Is there
The-
any information?
Concentration of those small molecules
Right.
around the
Yeah.
protoplanetary disk.
So I guess what denominator do you want for concentration?
Cubic miles? I'm not-
It's pretty dilute.
It's pretty dilute.
Yeah.
Whatever, I mean, whatever, what's common, what does she do? What do they do? As if they even ask them. Ask them.
I think you showed us a slide where you showed some density numbers,
were there
one of the
density-
early slides or something, that could maybe.
Oh, so I showed the density of like interstellar space is like less than 10 to the 11 or 10 to the 12 particles per cubic centimeter. So it can be as low as like 10 to the 4, or it can be as high as about 10 to the 12. But even that is sort of, in a lot of cases, less dense than the best vacuum that we can create on Earth.
Mhm. Mhm. So that kind of gives an answer.
Yeah,
Which one last question, I don't know if I missed it. What happens when these molecules get formed, in her experience? Do they fall apart? Do they stay together? Like how stable are they?
In her laboratory experiments.
Yeah.
So in your laboratory experiments, do your molecules disintegrate? Do they fall apart? What happens to, yeah, when they get hot?
Oh, when they get hot. I
Yeah.
mean, so they're never really getting hot. We heat them up to about room temperature, at which point they sublimate into the gas phase, well below that actually. But yeah, like a molecule like water or methanol or something like that is still stable at room temperature. So even when they go into the gas phase, they won't break apart. You would have to get to much, much higher temperatures to thermally dissociate the molecules.
Okay. Yeah. So Anders has a question. Is it possible to know how often planet formation is occurring in your galaxy? But he meant, oh, wouldn't that be something if you have your own
Well,
galaxy?
in my galaxy.
Oh my gosh.
one better than-
I know.
Yeah, so I can't exactly answer this, but I can say that it seems like most stars that are similar or lower mass than our sun have at least one planet. So, and those make up the vast majority of stars in the galaxy. So most stars probably have planets. I don't know how many
Okay.
are forming at any given point in time.
Right.
But it seems to be a very common outcome of star formation.
Okay, okay. Other questions? So do you have summer research opportunities for undergraduates?
Um, so, well, right now it's a little bit tricky because I'm still building my lab at Berkeley. So the
Right.
opportunities for undergrad research is a bit limited at the moment, but hopefully in future years, that would be a great thing to, yeah, to be able to do.
But what about graduating seniors that might be interested in joining your group?
Yeah, I would
Asking
say
for
to
somebody.
send me an email and we can discuss.
Okay, there you go. Open invitation, send the email. We have her email address. All right, other questions? Very nice. Thank you so very much.
Yes.
Yes.
Yeah, thanks for having me.
And we
All right,
thank our
take care.
physics. Yes. We thank our physics friends for joining us too, and you guys are always welcome to join. All right, take care.